I'm Melina. I'm working in the group of Trevor Forsyth, and for the Kiel University we are here at the ILL to do neutron structures. And this project here is a protein that is involved in a disease that is similar to Alzheimer, which is very well known. And it's a very stable protein, enzyme, very abundant in all humans, and at a certain point of time it degrades, and we don't know why it does, and it forms fibers like in Alzheimer, and it causes this mental disease. And our aim here is to find out why it falls apart, because it does not degrade prior to fibril formation. So what we want to see here with neutrons is how this protein sticks together, because it's a homotetramer, means that there are 4 proteins that form one entity, and at a certain stage it sort of falls apart. Here we have the map, the X-ray map of the protein, and you can see that, well, you can assume from this picture that here there must be a hydrogen bond, but you cannot see it because you cannot see the protons in X-rays. And when I switch on the map we got from Neutron data and switch off the X-ray map, you can clearly see that here is something. And this is that we can see the hydrogen, which has been replaced in our case by deuterium, and it scatters, and so we can clearly see that here's a hydrogen bond that stabilizes the protein. And especially we are looking for these interactions on the interfaces of 2 proteins. So they stabilize the complex, and we learn more about the protein.
My name is Selma Maric. I'm Swedish, but I'm doing my PhD in Copenhagen in Denmark, where I'm working with these so-called nanodiscs, which are like little tiny devices, a piece of membrane, the lipid bilayer surrounded by a membrane scaffolding protein, and we are trying to deuterate this so we can do structural studies.
At the moment my task is to grow very, very large crystals for one of the projects that we have here at ILL. The idea of the project that I'm working on is to grow large crystals on one side, and on the other side is to grow the crystals of per-deuterated protein. Why per-deuterated protein? Is because per-deuterated protein contains deuterium atoms that have the advantage when they are exposed to neutron radiation to not have an incoherent scattering, so we have a much better quality of the data at the end. And we want to see what are the limitations of using crystals under that contain the deuterium.
Okay, so come in. So this is the crystallization room.
So those are the dioxin crystals that we are trying to grow as big as possible. The main problem that we would have if the crystal was not per-deuterated is because of its larger and larger size. There will be much more absorption of the neutrons during the analysis.